Ah, yes, work energy, my favorite. So now we did these back in the first homework. So let's see, we got an alpha particle here, which I'll call Q1, which has a charge of plus 2e, and it's being fired at this great big gold nucleus. Q2, which has a charge of plus 79e, and the alpha particle gets close, and then it turns around. It reaches some minimum distance, r min, at which time it has a velocity of 0. Right? This is like a max height problem, so when it reaches that minimum distance, it stops instantaneously. And we know that r min, we're given that, is 7.2 times 10 to the minus 15 meters. Okay? And what we want to know is what is the initial velocity of the alpha particle. This gold nucleus over here is fixed. Okay, well, so there are a couple of ways to do this. One way to do it is to say, well, since there aren't any non-conservative forces here like friction or applied forces, that mechanical energy is conserved. So I can write that the total mechanical energy is conserved. I'm not a fan of starting there because that's not always true. Instead, I would prefer to say the sum of the works done by all the forces is equal to the change in kinetic energy. And in this case, there's only one force at work, and that's the electric force. And so I would prefer to write it like this, where the work done by the electric force is minus the change in electric potential energy. And we have to use this change of potential energy formulation because the force is not constant, right? It's a varying force. The force depends inversely on r squared, and since the force isn't constant, we can't use, you can't say that the work done by the electric force is equal to F delta S cosine theta. Right? That only works when the electric force is constant. So we're kind of stuck. We have to use this minus delta UE. Okay? And so this formula becomes minus delta U, which is final minus initial, is equal to delta K, which is final minus initial. Okay, so we get UI minus UF is equal to KF minus KI. And if you rearrange this, you're going to get that, right? You're going to get UI plus KI is equal to UF plus KF. Okay, so I know that KI is my unknown. That's what I'm looking for. I'm looking for that initial kinetic energy. KF is 0. Right? It stops when it gets close. In addition, we know that U initial, right, it's fired from some very large distance, very large R. And so the initial potential energy is 0. Because the form for potential energy, as we'll see, the final potential energy has the form of K Q1 Q2 over R. Right? And since R is very big, then UI is very small. But now here, the final potential energy depends on R min. Okay, but I can actually calculate that. I've got all the numbers I need. I've got 9 times 10 to the 9 for K, and then Q1 is 2E, and Q2 is 79E. I could have been lazy and just squared this, but I figured I'd write it all out. And I divide by R min. Okay, and that is 5.056 times 10 to the minus 12 joules. Okay, so I've got Ki plus Ui. Oh, sorry, it's Ui plus Ki. So 0 plus Ki is equal to 5.056 times 10 to the minus 12 plus 0. Right? So Ki is equal to that. And now Ki is 1/2 mv squared. So I'm going to set 1/2 mv squared equal to 5056 times 10 to the minus 12. Now the mass, this is an alpha particle, right? So the mass is 4.002602 AMU, and I've got to convert that into kilograms. I got to have everything in MKS units here. So that is 6.64 times 10 to the minus 27 kilograms. Okay, so now I can finally get this thing here. I get v squared is equal to 5056 times 10 to the minus 12 over 1/2 m which is gives me my velocity v 3.9 times 10 to the 7th meters per second. Now that's a little bit faster than I would like because it's into relativistic speeds, but as they say, it's when you're at a tenth the speed of light, relativistic effect is only 1%, and that's close enough for government work. So we'll accept that answer.